Ever wonder what's holding up those massive trains you see rumbling by? I mean, it's more than just the tracks, right?
It's a bit like an iceberg, isn't it?
Exactly.
Most people only see the trains, but there's this whole hidden world beneath the surface that's crucial to making it all work.
We're about to take a deep dive into that often overlooked foundation, the railway subgrade, and see how it impacts everything from speed to safety to the environment. You've sent over some fascinating technical documents on the topic, and I can't wait to unpack this with you. So, just like a house needs a solid foundation, so does a railway. But instead of concrete and steel, we're talking about dirt, rocks, and some surprisingly sophisticated engineering. So where do we even begin with something as seemingly simple as, well, ground?
It all starts with understanding that not all ground is created equal.
Right. I know.
That's where the classification system comes in, from S0 to S3, and even the R for rocky subgrades, each with its own quirks and challenges.
Right. I noticed those classifications in the documents. It's like a grading system for dirt, with S0 being the, well, let's just say you wouldn't want to build your dream railway on that.
You've got that right. An S0 subgrade is about as stable as a sandcastle in a hurricane.
Hmm.
It's all about how well the soil can handle the weight of trains without compacting too much or shifting around.
Okay, so how do engineers figure out what type of subgrade they're dealing with? Is it as simple as just looking at it, or are there tests involved?
It's a bit more involved than just eyeballing it, although visual inspection is the first step. They use a bunch of methods, including soil analysis. One key measurement is the California Bearing Ratio, or CBR for short.
CBR. Okay, I'm getting flashbacks to high school physics here. Break down for me, what does this CBR tell us?
Imagine pressing down on a sponge. A high CBR soil is like a dense sponge. It takes a lot of force to compress it.
Okay.
A low CBR, on the other hand, is like a flimsy sponge. It gives way easily under pressure. And this is crucial for railways because you don't want the ground beneath the tracks to compress unevenly as trains roll over them.
That makes perfect sense. So a higher CBR means a stronger subgrade, which is especially important for high-speed rail lines like the ones you mentioned you're interested in, right?
Absolutely. Those sleek, high-speed trains require incredibly stable foundations. Even the slightest bit of unevenness at those speeds could be disastrous.
I can only imagine. The source also mentions something called a plasticity index. Now, this sounds even more complicated than CBR. What's the deal with that?
Don't worry, it's not as scary as it sounds. Think about Play-Doh and how easily you can mold and shape it. That's high plasticity.
Yeah.
Now imagine trying to do the same with a dry, crumbly cookie. That's low plasticity. We need to know how the soil will behave when it gets wet or dries out because that affects the subgrade's stability over time.
Okay, that analogy definitely helps. So too much Play-Doh soil under the tracks could spell trouble if it rains a lot.
Exactly. And that's where good drainage comes in, but we can dive into that a bit later.
Sounds like a plan. Now, I know you sent us some information about what engineers do when they encounter a less than ideal subgrade. It can't always be smooth sailing, right?
You're absolutely right. Sometimes nature needs a helping hand, which is where things like geotextiles come in.
Geotextiles. Okay, I have to admit, that one sounds a bit intimidating.
Think of it like a heavy-duty fabric mat, almost like a giant coffee filter that goes between the subgrade and the ballast.
A giant coffee filter for the railway. I have to admit, I never thought about it that way.
Yeah.
But it makes sense, right? Keeping those layers separate so everything stays in tip-top shape.
Precisely. Geotextiles are surprisingly versatile. They help with drainage, prevent the subgrade from mixing with the ballast above, and even add a bit of reinforcement to boost the load-bearing capacity.
It's amazing how something so seemingly simple can make such a big difference. Now, speaking of challenging subgrades, what about those areas where the soil is just really bad, like that S-seer we talked about? Do they ever just scrap the whole thing and start over?
Sometimes that's the best option, but other times they can use clever techniques to improve the existing soil. The document mentions something called reinforced soil, which sounds like something out of a science fiction movie.
Reinforced soil.
Yeah.
So are we talking about like injecting the ground with super strength serum or something?
Not quite. It's actually a really elegant solution. Imagine building a retaining wall, but instead of using concrete or steel, you create it within the soil itself.
Okay, I'm intrigued. How does that even work?
They basically layer in these high-strength geosynthetic materials, remember our giant coffee filters, as they compact the soil. It's like building a sturdy, invisible wall layer by layer.
So it's like giving the soil its own internal support system. That's pretty ingenious.
It is. And in many cases, it's a more cost-effective and environmentally friendly approach compared to traditional retaining walls.
I'm seeing a theme here. Those geotextiles are the unsung heroes of the subgrade world. But even with the best materials, water must be a constant headache, right? It's not like you can just throw a tarp over miles of railway tracks.
I hit the nail on the head. Water is public enemy number one for a stable subgrade.
Right.
If water accumulates, it can turn even the sturdiest soil into a soggy mess, reducing its load-bearing capacity and potentially leading to those disastrous sinkholes or washouts we've all seen on the news.
Yeah, I definitely wouldn't want to be on a train if that happened. So how do they combat this constant threat of water damage?
It all comes down to meticulous drainage design. The document highlighted the importance of not just ditches and culverts, which we're all familiar with, but also a deep understanding of the local hydrology.
Hydrology. Now, that sounds complicated.
It's basically the science of how water moves. Engineers need to consider things like rainfall patterns, groundwater levels, and soil types to design a drainage system that can handle whatever Mother Nature throws at it.
And speaking of Mother Nature, the document mentioned something about the French high-speed line TGV Méditerranée and how real-world observations were crucial. What was that all about?
Ah, yes. That's a great example of why relying solely on theoretical calculations can sometimes backfire. They initially used formulas to predict how much water runoff they'd get during storms, but it turned out those calculations were way off.
Uh-oh, that doesn't sound good.
Luckily, they caught the discrepancy during the design phase. They had actually been collecting real-world data on water flow in the area, and it turned out the actual amount of water was significantly higher than what the formulas predicted.
So those real-world observations saved the day.
Absolutely. They ended up significantly increasing the capacity of their drainage systems based on that data. It's a great lesson in the importance of combining theory with practical experience.
And a good reminder that sometimes Mother Nature has a mind of her own. So we've tackled the challenges of soil and water, but what about plants? They always seem to find a way to take root, even in the most unlikely places.
That's a great point, and it's actually something the document spent a good deal of time on. Vegetation control is a crucial part of subgrade maintenance. You don't want tree roots cracking the soil or dense vegetation blocking drainage systems.
Right. Yeah, I could see how even a few stray weeds could cause a headache for railway engineers. What's the typical approach to keeping all that greenery in check?
Well, they have a few options, each with its own pros and cons. Herbicides are commonly used because they're effective, but there's a growing awareness of their potential environmental impact, so there's a lot of research going into finding more sustainable alternatives.
That makes sense.
Yeah.
What are some of the alternatives they're exploring?
One option is laying down an asphalt layer beneath the ballast to create a physical barrier against plant growth.
So, like paving the way, literally, for a weed-free subgrade.
Exactly. But this approach isn't always feasible, especially in areas with sensitive ecosystems or where costs are a major concern. Another intriguing possibility they mentioned is using targeted radiation, like infrared or microwave technology, to control vegetation.
Now that sounds like something straight out of a science fiction movie. Are we talking about blasting weeds with lasers here?
It's not quite laser beams yet, but the idea is to use these technologies to disrupt plant growth in a targeted way, minimizing harm to the surrounding environment. However, the document did mention that these methods are still in the experimental phase and need further development before they're ready for widespread use.
It seems like even railway subgrades are on the cutting edge of technology. But let's shift gears for a moment and circle back to those herbicides you mentioned. I'm curious to know more about how they ensure responsible use, especially with environmental concerns in mind.
That's a crucial point, and it's something the document addressed directly. It emphasized that minimizing environmental harm should always be the top priority when using any kind of herbicide.
So it's not just a matter of spraying and hoping for the best.
Definitely not. They have to consider factors like the proximity to waterways, residential areas, and sensitive ecosystems. Plus, there are strict regulations in place to govern how and when herbicides can be used.
It sounds like they're taking a very cautious and measured approach. Are there any specific techniques they use to minimize the impact?
One interesting thing they highlighted was the concept of the spread factor. Imagine you sprinkle pepper on your dinner, ideally. You want all that pepper to land on your food, not on the tablecloth.
It's all about targeted application.
Exactly. The spread factor basically measures how much of the herbicide is actually absorbed by the soil versus how much might drift or leach into the surrounding environment. The document mentioned a target of 150 or higher, meaning the majority of the herbicide stays put.
So the higher the spread factor, the less likely it is to end up where it shouldn't be.
Precisely. It's all about minimizing that environmental footprint. And it's not just about where it lands, but also how long it takes to break down. Ideally, these herbicides should degrade relatively quickly, within 9 to 12 months, to reduce any long-term effects.
That makes a lot of sense. It seems like they're really trying to find that sweet spot between keeping those tracks clear and being responsible stewards of the environment.
Absolutely. And this is where we come full circle. Remember how we talked about the importance of good drainage for a stable subgrade?
Yeah, it was like the first rule of Railway Subgrade Club.
Well, it turns out that a well-drained subgrade doesn't just prevent water damage. It can also significantly reduce the need for herbicides in the first place.
Now, that's what I call a win-win. Less reliance on herbicides and a more stable track. Who knew that good drainage could be such a powerful tool in their arsenal?
It all comes back to that interconnectedness we've been talking about. Every aspect of subgrade design influences the others, and it highlights how innovative engineering can lead to more sustainable solutions.
Absolutely. We've covered so much ground today, from soil types to geotextiles to the challenges of water and vegetation. What stands out to you as the biggest takeaway from our deep dive into the world of railway subgrades?
For me, it's the realization that something as seemingly mundane as the ground beneath the tracks plays such a pivotal role in the entire system. It's a testament to the ingenuity of engineers who work tirelessly to ensure the safety, efficiency, and sustainability of our railways.
Couldn't have said it better myself. It's a classic case of out of sight, out of mind. But now that we're aware of it, we can appreciate the hidden complexity and importance of the subgrade. So as we look to the future, with the demand for faster trains and heavier loads only increasing, what innovations do you think we might see in the realm of railway subgrades? Will we one day have self-healing tracks or subgrades that adapt to changing environmental conditions in real time?
Now, those are some thought-provoking questions. I imagine we'll see a continued push toward sustainable materials and construction techniques, perhaps even incorporating bio-inspired designs that mimic nature's own solutions. The possibilities are truly exciting.
It's exciting indeed. It seems the future of railways is not just about what's on the tracks, but also about what lies beneath. We'll have to keep our eyes peeled for those groundbreaking innovations. But for now, we've reached the end of the line for this deep dive. Thanks for joining us on this journey beneath the surface. Until next time.